Good morning to everyone. In today's video we are going to see the transmission lines part 2 unit. So here the first topic is your input impedance relationships. So here input impedance relationships, we have a small derivation related to your input impedance. So already you know in our previous videos whatever the transmission line voltage and current will be represented in terms of your incident and reflected voltages. So here the voltage equation will be provided at as V equals to V1 e power minus gamma x plus V2 e power gamma x. So here the first term represents your incident voltage and the second term represents your reflected voltage. Similarly for your current also it will be represented with the incident current and reflected current. Okay. So here if you are considering a transmission line, if you're considering a transmission line, one end will be termed it as a source and another end will be termed it as a load. So here we are taking the load as our reference point. So here the distance x equals to 0 at load, and for total length of the transmission line is L. At source end the distance will be termed it as minus L. Okay, so if you replace these values, that is x equals to 0 and x equals to minus L, you can able to get what will be the voltage at your source and load ends. So here first of all we are finding the voltage and current at load terminal by considering x equals to 0. So when you replace x equals to 0, e power 0 is nothing but 1. So V is nothing but, voltage at load terminal is nothing but Vi plus Vr. At the same time current IL equals to II plus IR. So because these are the incident and reflected voltages. Similarly for your source terminal also we just replace X with minus L. Find out what will be the source current and source voltage. So as we know that the impedance the characteristic impedance Z0 is nothing but Vi divided by II or Vr divided by IR. So nothing but either the voltage, the ratio of voltage and current either at source end or load end is nothing but your characteristic impedance, and the reflection coefficient is nothing but the ratio of reflected voltage to the incident voltage. So now we placing the input impedance Zn is equals to Vs divided by Is. Already we have the equations for your Vs and Is, so try to replace those equations. So from these equations if you find out what will be the solution, then you can get the input impedance of a normal transmission line. Or if you replace this transmission line with the lossless transmission line, here lossless transmission line is nothing but your attenuation constant equals to 0, then the gamma is nothing but alpha plus j omega beta. So if alpha equals to 0, j beta is replaced with omega is whatever the gamma is there, it is replaced with j beta. Okay, so I just replace these equations with gamma equals to j beta, and we know that whatever reflection coefficient from your characteristic impedance. Okay, so Vi equals to Z0 II and Vr equals to Z0 IR. So we replace those values and taking this one in commonly in current equation. So Vi replaced with Z0 II and Vr replaced with minus Z0 IR. So once you got this, you can take it common the Z0. Now we have the expression in terms of currents. So by using your reflection coefficient, we making it as a common in terms of reflected current. Okay, so IR equals to minus reflection coefficient into II. So now the expression is in terms of incident current II. So take it out common and cancel over to each other. So numerator and denominator will cancel over. So that our expression will be Z0 into e power j beta L plus reflection coefficient e power minus j beta L. Already in our last class we seen the reflection coefficient, because that's why the reason I just started the reflection coefficient just to have an idea. So reflection coefficient equals to ZR minus Z0 divided by ZR plus Z0. So replace that value and find out and replace that. So when you replace this, here the denominator is Z plus Z0, cross multiply, take it at common denominator. This denominator and this denominator will be cancelled over. So the leftover expression is here. From here, take it out common, the ZL and Z0. ZL and Z0. Now this expression will be in form of your sine and cosine values. Okay, so try to replace those values. Okay, try to replace those values and take it out the common of 2 cos beta L. So it will become 2 will be cancelled over. Sin beta L divided by cos beta L will be tan beta L. So this is your normal input impedance for a lossless transmission line. To take it as a normalized impedance, because in Smith charts we are using the normalized impedances. So to calculate the normalized impedances, you have to divide with Z0. So if you divide the entire equation with Z0, here this Z0 and Z0 will cancel over. So this will be input impedance normalized value plus ZL divided by Z0 will be the load impedance normalized value. So the leftover expression is the normalized impedance. So that's it for your input impedance, and this is for lossless transmission line. Thank you.